Okay, in this tutorial, we will cover how to set up a custom tool. So our Kuka is very specific about how it wants a tool mounted. So the first things first, if we're setting up a custom tool, we need to actually model that tool. So for us, we will set up a custom pen tool. So what we will do, we will import our adapter file. So I'm just going to navigate to where I have saved my adapter file. This will also be included. No, let's go back. Our QC11 tool mount and adapter. Okay, because I'm in feet and inches, we want to get into millimeters just to make sure everything's right. Yes, we can scale the model. Now we have our tool mount. Let's change it to shaded view. Alright, so whatever we want to actually model, we need to make sure it is precisely mounted on this tool mount. So one thing we can do, we can hide this and actually model what we want to actually go on top of that tool mount. So actually, let's bring it back. So what we can do, we can get the edges of this, because what we're going to actually do is build a circle on top of it. So let's do the actual circle here. Let's do those edges, duplicate them. So now we have two edges, two curves. We're going to join it. Okay. So let's extrude this. We want to make it solid. We're going to close it. Both sides no. And we already have the tab set. So let's do 10 millimeters just to be safe. Okay. And then we can scale it from the center. So find that center point. Find the edge point. Should actually look at the top view. We need is actually we need to actually create a point to actually map our geometry we're going to model. So I'm going to do area centroid, get a point. I make a point here. We can do the same on the surface. Same command. And now we can just move it down. Okay. For actual simulation purposes, it doesn't have to be exactly perfect. We don't have to model a pin completely. We just need to make sure the actual height is actually correct. So what I will do, I'll create a cylinder that actually kind of represents our geometry, and I will model it so I know the actual height of this part of the tool. The height from the base to the tip. So again, I'm going to pull yeah. From here I'm going to actually pull that center point for a circle. Boom. Doesn't have to be too big. Let's do 5 millimeters. Didn't do it. Let's try it again. Circle. Center point 5. And we can extrude this up so it matches our intended height. This is the height that we will measure. I measured it at 70, so I measured the overall height from 70. So, and this is polyline measuring. This is 10 roughly. I know I need to actually make it 60, so I'm gonna extrude this up 60 for our actual simulation. So once you have your tool geometry actually on here, this can be more precise or more abstract as you want. It's only for simulation purposes as long as you have the correct TCP tool center point wherever this point is. Actually, do area centroid again. Wherever the point is at the end of this tool. So for our purposes, we need to find the accurate TCP, which is the tool center point, the point along at the end of this tool. So after doing area centroid, you can find that point here. And yes, so in Rhino, we have this geometry already set up for us, our base mount for our tool mount and adapter for the actual robot. And we need to, because we're doing a custom tool and we're doing a manual measuring method, we actually need to tell the robot where this point is. We can't do that necessarily in the real world as far as measuring goes, because this mount right here is already attached to the robot. But what we can do is measure this point to this point, which we know is 70. We did that in the real world manually. And we can find the actual length from this point to the actual origin to find the actual length of the tool. So once we do that, all we have to do is hide this and get a polyline or use the distance command to figure out how long our tool is in the Z direction. And it is 138. So we know it's 138. What we can do now is record that for later. So now we have a custom tool set up. We know that it's 138 millimeters, and we can now put this into our simulation. So I'm going to show this and pull it up. So the next step, we need to mesh it, and once we mesh it, we need to join it for our simulation. So I will save this. Actually, let's mesh it now just to be safe. We can group this, make a new layer. It's called layer 1, our poly surface layer. And we can change our layer. Change layer. We'll move all that we have selected to our poly surface layer. Set that as the current layer. Oh, we need to move this to this on poly surface. Yes. Group, make sure. Display color. You can do by layer, just for that, make sure. Yeah. So now that we have it all on the poly surface layer, we can mesh it. So we're just gonna type of mesh. Mesh actual geometry doesn't matter for this. We just need to make sure it's a mesh for our simulation. Now that everything is meshed, we can actually change this layer. So what I'm going to do, I'm going to select all the meshes. I'm gonna change this to layer 2. Change layer 2's name to mesh, and change the default. I'm gonna hide this. So now we have everything as a mesh. Now we need to join the meshes. When we click on the KUKA PRC core component, it will ask for a tool. And once we put in a custom tool component, the custom tool component will ask it to be a joined mesh. In Grasshopper, you can join it through mesh join. In Rhino, it's just a simple join command. So we're just going to type in join. It's going to join it into one closed disjointed mesh. You can now save this as our custom tool, and we'll call it custom pen tool, and we will put it where we need it. I will do it in my KUKA PRC license folder. Okay. All right. Now we need to import this into our working cell geometry file. So the file we will do once we have, now that we have meshed our geometry, we need to move it into our working cell geometry file, the file where we are doing our simulation. So I saved it. I'm going to pull up our RPL cell. This could be any file as long as you have your cell in it. It's also moving some, so Grasshopper. I'm going to turn off our preview. Preview's off now. Okay, we can minimize it. So in order for the tool to map properly, we need it to be at the origin, the world origin, which it is now. So when we import it, it'll automatically go there because that's where we modeled it at. So when we import our tool, it will automatically go to the origin because that's where we modeled our tool at. So we're going to grab our custom pen tool. We're going to open it. We're going to automatically, okay. So yes. So now that our tool is here, we know the actual height. We don't actually need to know our actual height at the moment. We still remember because you wrote it down as 138 millimeters. Select it all and open up Grasshopper. So we know we have imported a tool component in our basic template. Let's save this as basic Rhino template. Let's save this as our KUKA PRC RPL template. Let's put basic. No, this one. Okay. With our geometry still selected, let's just open up another geo component and select one geometry since we know it's one mesh. And we're going to need a custom tool component. So let's just type in custom tool. Bam. So custom tool component asks for geometry. So it knows it needs a custom tool geometry and we know it needs to actually have the tool geometry along the lines of the positive x. We oriented that as from the origin up to the vertical z direction based on our actual mount template or mount file. So once we have selected our tool geometry, we know that our custom tool geometry needs to mesh. It says it needs it along the positive x direction. Right now it's along the positive z direction. It only asks for it to be along the positive x direction in order for it to properly map, but based on our adapter file, we know that it is correct. We will get into why this is the way it is once we start doing the simulation. This will involve some plane manipulation or in order for the tool to properly hit where we want it on the file. So geometry to geometry, we're going to put the tool in here, and from here, once this, why is it? Set tool properties via right click settings. Okay, so now we need to set the tool. So in order for this to turn orange, we need to actually set our actual tool. These numbers can either come from a manual calibration or the tool calibration on the Kuga, where you will track these numbers based on the tool calibration from the Teach pendant. Because this is just a simple tool going in a positive Z direction, we know where this TCP is. TCP is 138 millimeters. So all we need to type in is 138 and hit confirm. Okay, alright, so we know over here it asks for the tool to be oriented along the positive X direction, and this is only because the robot is configured so the X is coming out. However, it's not shown here. So in order for it to actually track right, we have two different options. We can either rotate it negatively along the B, so we can rotate it 90 along the B direction. So the B rotation, we can set it to negative 90, and that will allow our planes to actually match our tool orientation, or we can manipulate our planes to match our tool orientation. For now, we will set this to 90. However, when we actually do the simulation, we will see how it works both ways. Okay. So now we have a custom tool, and we have it mapped to our robot. So let's close this out. You can see our end effector now has a tool on it, which is this right here. We can hide it now, and I can explain what's going on. Let's select, turn on that preview. Okay, so we know that the Z right now is oriented this way based on the negative 90. However, we were to set it to 0, I'm pretty sure that would change. Yeah, if we set it to 0, the negative 90 is no longer in the tool direction. It's actually based on the world. That means if this was to point down, it would actually hit the X instead of the Z, where we actually want it to. So, like I said, we can either manipulate our plane, which we would get into, or manipulate our tool. So, the more complicated way is to manipulate the plane. So, let's go ahead and try that option first. I'm going to confirm our tool, and now we can actually set up our 2D drawing. Now that we have mapped the tool to our robot, we can actually proceed with doing an actual simulation. We move the slider, we can see that now the tool is actually mapped to the robot, and It works. Now we can actually do something more complicated like a 2D drawing.